Alright guys, thank you for clicking on the video today. As I'm sure you can tell by the title of the video, we're going to be designing and 3D printing a new intake for my 2005 Subaru Outback XT. I haven't made any videos yet on my design process and actual printing process, so I figured some of you might be interested in how I go about designing stuff and printing stuff, and material choices and so forth and whatnot. So I figured this would be a good video to do that on. My Cobb SF Intake, carb legal intake, the MAF housing was too small and it was maxing out the MAF sensor. So in order to get all the power that I want out of that big turbo, I either need to convert to speed density, which comes with its own drawbacks, or get a larger MAF housing. So being is that I want to keep the car carb legal, I really wanted this intake, but it seems as though this small diameter MAF housing is the limiting factor. And I was kind of afraid of this from the beginning when I first started tuning with this, because I noticed that you could put this intake on and you don't need to tune. You can put it on a completely stock car and the MAF scaling is the same. So that kind of worried me from the beginning. I was like, I don't know how much power this is going to support, and I was right. So what I'm going to do is I'm going to replicate this MAF housing so that its fit up is the same here, and the MAF sensor, but the diameter is larger. So I'm just going to basically mimic this design so that it fits with all the other Cobb components, but has a larger MAF so that I can actually make the power I need. I like to use Fusion 360 for my designing. So I was actually an engineer for a little while in college. I learned how to do CAD on Creo and SolidWorks, and Fusion 360's interface is kind of similar to those, but it's just, I think, more user-friendly, so it was an easy switch over for me. So that's one of the reasons that I use Fusion 360. I like it. And then also they offer a, if you look up here, they have a personal use, which allows you to have 10 open projects that you can edit, which is perfect for anybody who's just designing stuff for themselves or any small businesses and stuff. But it's free. The personal use Autodesk Fusion is free, so it's really good software. It's free, has some limited features, but for everybody, it's pretty much good enough for what you need it to be. So that's why I like Autodesk Fusion 360. I'm just going to kind of try to walk you guys through the design process of this. So what I'm going to do first is I'm going to create a new sketch. There's a couple ways you can design this. The first way I'm thinking of is finding the diameter that I want and drawing that circle and extruding that up however high, and then from that sketch I can draw these features and stuff. But I think what a better method of sketching this would be is to draw a sketch of it this way, like cut this in half and draw this shape here. If you were to look at a cross section of this shape, construct this shape with the correct dimensions, and then extrude it in a revolve so it creates this circular appearance. So I think that's what I'm gonna do, and then once I have this shape extruded out, I will pick a spot and I will add the feature for the MAF sensor. I don't think I'm going to do these straighteners. My old intake didn't have it, and I'm sure it has some sort of beneficial effect in sensor readout and stuff, but I feel like it will just complicate the model, so I think I'm just going to leave it out. Plus I would be afraid, these are very thin structures, so with the 3D printing I'd be afraid of these breaking off and going into the turbo, so I'm going to leave those out. So my old intake had a diameter of 73 millimeters. This one is kind of bent. It looks like it's like 67, 66, somewhere in that range. And I'm kind of thinking of maybe doing 75 just to give it a little extra space. And then worst case scenario, if it doesn't work or I don't like it, I can change it up. So we want our inner diameter to be 75 millimeters. So I'll do 75 divided by 2, so that'll be half of 75 because I don't want to do the math. So that'll be our diameter for the base, and then this guy is 131.25 is how tall it is from here to the base here. From that spot I just need to directly measure this, because my plan was to use the filter element that came with the intake. So that looks to be 113 It's like 113.40. Okay, so this will be 113.40 divided by 2. And then we'll get the height here. And I can do this the same way. Just measure down. 18.20 for this lip right here. I'm just going to sketch out 2.5 from that initial measurement. I'm going to go up 2 and then back over 2.5, and then from there we'll do the 18.20 straight up. And now this does kind of have like a velocity stack shape to it, but I think I'm gonna do that feature later. So for now, okay, so I'm just gonna take this feature and come straight out, and then I'm gonna go straight down. Okay, so we have this shape. So these dimensions up here are correct to match this. This section right here is actually the inner diameter, so I need to base off of this, decide how big I want my wall's thickness to be. And I think probably what they have here is probably good. So theirs is like 3.6, so I'll do 4 millimeters of wall thickness. 4 millimeters. So we'll do that. So there's our wall. This needs to fit into the factory silicone coupler. So the diameter that goes into the coupler needs to be the same, and then I'll have to step it up to the MAF. So I need to measure this outer diameter and match that up at the bottom here. So this measurement is saying 73.85, and this measurement is saying 75.70. So we'll say 74 and then meet in the middle there. It's very close to our inner diameter, so I think I'm just gonna have like the inner diameter kind of step up this way. We want the wall to be 4 millimeters, and then I need to figure out how high I want this to be. The coupler goes like all the way up to the pipe right here, so we're gonna have to have a really big step. So it's gonna be a 40 millimeter step. Oof. Okay. Get rid of that line, draw a new one. There's our step. This will be where it's smooth. So I'm gonna work on the top here. So we'll draw this guy to be straight up. Okay, so that's straight up. Delete this line, redraw this, so that goes to there. Now, I got the kind of basic sketch of the cross section. So I'm gonna go in and do some smoothing. So I'm going to use this fillet tool here. Did this radius right here. Right here. We'll do this guy. And I'll do a 4. 4 looks good. Now we just need to smooth this guy out. This can't be this small here, so I need to do like a... Okay. 3, I'd call that good. This guy, I want to put a little bit of a curve in it, just like a 0.5. There we go. So now I'll redraw this line, smooth this out. We'll default that, just make that smooth, and then I'll make this guy smooth right here. That looks good. Okay. Anything else? Let's do this one. Okay. So all of our edges are smooth. Everything looks good. So now we'll do a revolve. So I'll finish this sketch. There's our finished sketch. And now we can click revolve. It's selecting this tool. New body, so we need to select the axis, so I'll put this as the axis, and there's our new intake. So this is what we're going to start with here. Looks pretty good. This might need to be smoother, but we'll figure that out. So yeah, so what we got to do next is sketch this design on there. I measured with this guy. This is kind of just an eyeball thing, but I wanted to figure out how far from the end was the center of the hole, so I just used this kind of, I don't know what you call that function, depth function, and I went down to where I was like, okay, it looks like it's in the center of that hole. and that measurement ended up being 77.5. Drew a line here to the center, 77.5. So it looks like the hole has a taper. It starts out as 31.5, and then as it gets to the bottom, it like kind of tightens up to like 30.75. I feel like we should probably incorporate that feature, but let's start with the hole here. Let's just do 31. Enter. The wall thickness is 3. 31 plus 6 is 37. That'll give us a 3 millimeter wall. So the tricky part's going to be figuring out the offset of these holes and their relation to the circle. If I measure the actual width of the MAF sensor, comes out to 40.65. 40.65 divided by 2. So that's the edge of the sensor. 40.35 tall. 40.35 divided by 2. So we'll hide that body just so to get it out of the way. Here's our basic square part of the MAF sensor. From that square measurement, I'm going to try and find these holes based on like wall thickness and stuff, because they are flush with the side here. Okay, so using the depth gauge, the top of here is 10 millimeters from the top of here. So I can draw a 10 millimeter line right there. And we know that's the top of this. So now we can measure our wall thickness, which is 2 millimeters, 2.15 there. I'm gonna eyeball the center line off the edge. So like when I eyeball measurements, sometimes I like to just like, okay, like I'm measuring it and it looks like it's like 6.08 or something. It's probably 6, because when people are designing stuff, rarely are they going to be using those weird increments of measurement. So I'm going to say the center line of this radius is 6 millimeters. I'm going to go 6 in, and then from the top, okay, so from the top we'll go down 2. Okay, so that's the wall thickness, and then we'll measure the diameter of this guy, and it's 8. So the center line from there will be 4. So it's also 6. So it's 6 from this side and 6 from that side. Or is it a little more than 6? It might be 6.15. There we go. Because this wall's a little thicker. This one's 2.15, and the top one was 2.0. I think this should be our center of the first hole. I think that's the proper location. So now we can draw how big we want this to be. So this is measuring 4.45. So we'll draw a circle, 4.45. Boom. There's our first hole. Now for the second hole, we'll try to do something similar. So as you can see with this one, this base here is in line with the rectangle that I drew earlier. So I can take the measurement of this wall and find the diameter like I did with the other one, and then do the measurements from there. And this hole is also the same size as the other one. I can measure the wall from the base, and it is 2 millimeters, and the wall from the side is 2 as well. I'm going to start here on this corner, so I'm going to go up 6. So that's center, and then I'm going to go over, and then from here I'm going to go over 4. And that's our center hole right there. Draw another 4.45. That marks the center. Since this is not actually the MAF sensor, those center measurements are not too useful. So I'm just gonna take how big they made this post, and it looks like it is a diameter of 13. I'll draw a circle with a diameter of 13 using the same center point for both of them. Okay, so I got these little M4 heat set inserts, which I'm going to use, same how they used heat set inserts here. So I'm actually going to change that center measurement to the diameter of this guy, 5.75. So we'll change this to 5.75, and same with this one, 5.75. Okay, so now hopefully this is enough information. We can finish sketching everything. Okay, so I selected the center hole, extrude, and we'll just do this, and you could put distance through all. Let's select our outer ring, and then we will click extrude. Okay, so we'll set our offset to 33 millimeters because that'll bring us right to the edge here. And then we're going to change this to join. We want this to be just above that. I think that's probably good, like that. Thumbs. Oop, 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 oop. Okay, selected all those. Bodies, extrude. Now I need to figure out what height these go to. Our exact measurement is 4.92, so maybe let's go with 5. So I think for this one we'll also do an offset plane of probably 33, and then let's get it to the same height. So there's our same height, 33, so we're at 9, which is what we previously extruded. And then we want to do 5 millimeters higher than this, so we're going to go to 14. 14, and then we'll do join, and those should be correct now. So now on the inside here, we got a little bit of a mess. You see these things poking through. So since we have these things protruding up through here, we're going to take a look at our sketch here, hide our body. So what I'm going to do is I'm going to edit this sketch. We're going to draw a line from here to there so that this box is connected. Finish sketch. Okay, so we'll select this shape. So it's just selecting the inside, and then we'll do a revolve cut. This axis, and now this cut will remove all that stuff that was sticking out here. So now we're all clean on the inside, and the outside is the right shape and dimensions. And this is about it. Alright, prototype number 1 is done. All that's left is to get this printed. So we're going to do the first print out of PLA just to check fitment and tolerances and stuff. And then once that's done, we can move on to printing it out of carbon fiber nylon. Okay, so right here I have Orca Slicer open. This is the software that I use for slicing my files to send to the 3D printer. I have a Bamboo Lab P1S, so this software works really good with that printer. So I'm just going to start a new project here. We're going to go up here, click here, and we're going to pick up our folder intake file. Now this part's pretty important. You want to orient your prints so that like structurally they're good as far as layer lines goes, and surfaces will print good. So I'm definitely going to need some supports because of these overhangs. This is the orientation that I wanted to mount it in, because I think this will yield the best print quality along with strength. On the left here, we'll select filament. I'm just going to do Bamboo PLA Basic. I like to select inner, outer, inner. That makes it dimensionally accurate the best. Supports, we're going to enable supports. And I like to use the tree supports and organic. We'll leave the rest all alone. So let's slice the plate, see what we get. So yeah. Put the seam right on the back there. Perfect spot for the seam. Okay, so yeah, this is pretty minimal supports. Honestly, this might work without supports, but it's kind of iffy. But the support shouldn't give too bad of a finish, and I think I'm going to sand this hole in the center as well. Also, another thing to think of is when you print small holes like this vertically, sometimes they cave in right here, even with supports. So if this hole is supposed to be like a pass-through hole, it might not fit the bolt correctly. So if you make these into like a teardrop shape, it keeps them from collapsing, and it makes it so that the bolt will pass through it and it'll be dimensionally accurate. But since I'm putting heat set inserts in there, if it's a little not the correct roundness, since I'm heating this up and pushing it through, it'll correct any slight errors, so I'm not worried about it in this situation. It'll just help with the hole being a little snugger. But that's about it. So let's get this started printing. It says it's going to take 3 hours, almost 4 hours. We got the final design done. So since I printed it out of PLA, checked the fitment, made sure everything fits together. I'm preparing the final part to be printed out of the carbon fiber nylon, the PA6 nylon. I made a few changes to it after printing it out of PLA. So this was done on the previous, but I just want to reiterate it. I just changed the profile of the velocity stack portion here to make it a little more steeper, so the airflow is a little better. I'm still not too happy with this step down here that I have to do to get to the silicone hose, but I can't really make the transition any longer because then I'll be getting into like where the MAF is, and I don't know how close I can get to the MAF without affecting the way that the diameter performs, since that's the whole reason I'm doing this. So I'm gonna leave that where it is, but I did make a little change to it that I thought was pretty neat. So this is the sketch that we revolved earlier, and before, this thickness right here between these two walls just came straight all the way down. So then there's like a little ledge here where some turbulence can be created at the end. So what I did, I matched the length of the slope here. So I basically created a little venturi. Since I had to neck it down anyways, I figured maybe a venturi will help, and it'll also keep the air from coming off here, being turbulent, and it'll help with the overall airflow. So we have our velocity stack profile here, and then next down to fit into the silicone coupler, and then opens back up into a venturi. I think this will work pretty well. Also, the reason I was able to do this, if I was clamping right here, this wouldn't be strong enough to clamp, I don't think. But there's so much real estate to clamp that coupler that I'll just put the clamp like right here, and I'll be clamping on the square part, and then this is just a transition to smooth out the airflow. So pretty happy with how this looks. Let me show you how it looks, like so. So you can see the venturi there. Pretty thin wall. Alright, so the part just finished. Came out really nice. It took a lot of trial and error and dialing in the filament settings to get it to print good. But I got a part that is workable. It has a few blemishes, but overall not bad. Just show you, ignore my messy desk. So I ended up printing this one this direction. My test piece I printed this way, and this was pretty bad. And then on my test print with the nylon filament, it was like really bad. So I decided to print it in this orientation so that I wouldn't need supports here, so that it would be smoother. It required a lot more support material, as you can see, but I think the finish is better overall. There's a couple blemishes. This section right here below this was old filament, and then this was brand new filament, so you can tell the brand new filament printed better. And then on the inside there's like a little bit of debris on the seam, but that'll be really easy to clean up. Got a really nice finish. The MAF sensor mounting areas turned out really nice. The holes will probably need some cleaning up, but looking good. The only issue is towards the end it started to, I think this like geometry is pretty hard, because normally with this nylon filament you want to have a lot of top and bottom layers, like 4 at least, because sometimes the first layer is not very good. But since this is like so stretched out, there's only like 1 or 2 layers right there, so sometimes you get some things popping through. So I just trimmed off like the high parts, and then some of these will be fine, but like these bigger ones that left like a hole, I'll probably come in and try to fill it with maybe some filament or something, melt some filament in there. But let's break off these supports and check it out. Really nice and satisfying. Yeah, and the only downside to printing it that way is that this surface right here is going to be a little bit ugly because that's where the support interface was, but that'll be all right. So you can kind of see the Venturi idea that I had. So I'll come in here and clean these out. I'll get a razor blade and cut them, but it'll be nice and smooth. Fill those in. That'll be good. I'm gonna get this cleaned up, and then we'll be back once it's cleaned up, and we could put in the heat set inserts and all these holes here. So I got the part cleaned up. I melted some leftover filament into the holes and sanded everything that was raised smooth, so airflow should be good now. Now I'm going to install the heat set inserts into these holes. So I got these little tiny brass inserts. They're threaded, so they'll be much stronger than if I were to 3D print threads. And 3D printed threads just don't print very well. But I have this thing right here, and it has this attachment that these heat set inserts go onto, and this is basically a soldering iron, and that it heats up the filament and melts the heat set insert in. So I'll try to show you this. It's already warm, so, and this comes with like a press, but I have to go handheld because this part's too big. Okay, those ones are good. Once those heat set inserts are in and cooled down, I can put the threads in, and the MAF sensor is in there really nice. And you can get these pretty tight and not have to worry about them stripping out because they basically bond to the plastic. This is the type of fastener technology that they use in a lot of OEM applications. So it's tried and true, it works. There's a reason OEM manufacturers do that. So they're in and they look good. So we got the MAF ones in, and we got the mounting ones in, and everything looks real good. This thing's ready to be installed. So here's the final product installed. I've had this installed for a little while now, and it's holding up great. No issues with tuning it, so everything seems to be sealed up and holding together good. The diameter I decided to go with for the MAF housing is like just big enough to fit in here. If it was any bigger, I don't think it would fit in here. I'd either have to remove this rubber or trim this to make it bigger to accommodate the larger diameter, but seems to be working good for now. So stay tuned for the MAF scaling videos, where I'm going to show you guys from start to finish how to do a complete MAF scaling tune for a new intake. So that will be coming up very shortly, hopefully in 2 weeks. Get yourself some high quality 3D printed car parts at swspeedco.com. I'll put a link here, and I'll put a link down below in the description. I hope you enjoyed the video. If you did, please leave a like. If you have any questions for me, leave them down in the comments below. If you aren't subscribed, please consider subscribing. And if you know of somebody who might like this video, please share it with them. As always, thanks for watching. I'll see you in the next one. Peace.